Welcome to the first week of the Potentiometric Titrations lab. This video is going to explain the two-step process that we are going to go through to try and determine the concentration of an unknown HCl solution. The very first step that we're going to do is we're going to perform something called a standardization on sodium hydroxide. So the reason that we have to take this first step is that sodium hydroxide is hygroscopic, which means that it absorbs water from the atmosphere. So normally sodium hydroxide, if you have a brand new sample of sodium hydroxide that you're pulling off the shelf, purchased from a chemical vendor, it'll be these nice sort of spherical shapes on the left-hand side of this slide. But over time, what happens is, as this container is opened, it gets exposed to the atmosphere, it absorbs water from the atmosphere, and it sort of turns to this mush and eventually begins to melt, like what we see on the right-hand side of this slide. Now, the reason this is important is if we weigh out some of this sample from the right-hand side, what we have is some water mixed in with our sodium hydroxide. So if you weighed out, let's say, 1 gram of the solid on the right-hand side, not all 1 gram of that sample would be sodium hydroxide. You'd have some water contained in there. So this process of standardization, what it does is it allows us to know just how much NaOH we actually have in our solution. So the lab starts out by telling you that you're going to try to make a solution that is 0.15 molarity. So you do a calculation based on a volume of that solution and that molarity, and then you begin to do the standardization to check what your molarity actually is. So the way that we check the sodium hydroxide is we use an acid that is not hygroscopic. And in this case, the acid that we're going to use is called potassium hydrogen phthalate, which is abbreviated KHP for short. And again, the reason we use KHP is it does not absorb water from the atmosphere. So we know exactly how much acid we have. We're going to react it with our base according to this equation at the bottom. So we have some NaOH solution. We have our acid solution here. They undergo a neutralization reaction where we measure, where we make water as one of our products. So you'll notice water here. Water does not affect the pH. We have a highly soluble salt here. This soluble salt also will not affect the pH. So what we know about this reaction is when the number of moles of our acid and base have reacted in exactly the same amount, we should have a neutral solution, or a solution which has a water does not show up on our reactant side here, pH of 7. So step number 1, what we're going to do is we're going to start with a known mass of KHP. So if you were in the lab, you would start by weighing out some KHP. Now you have a mass of this, you can convert that to moles. Then you're going to dissolve this KHP in some water. And what's pretty interesting about this reaction is the amount of water that you dissolve this in doesn't really matter, because if we go back to the previous slide, so you dissolve your acid in some water, and then what you begin to do is you begin to add to this acid the sodium hydroxide solution that you had made. So the idea is you add sodium hydroxide until you reach a pH of 7, because at that pH, what we know is that we've reacted all of our acid with all of our base. So the way that we know that we've reached a pH of 7 during the standardization is we use phenolphthalein. So you might remember this from your lab in Gen Chem 1. This is exactly the same sort of thing that you did back in Gen Chem 1, where we started with an acidic solution. So we have our KHP, which is colorless, and you begin adding sodium hydroxide, and eventually what you hope to get is a very slightly pink solution color. And the reason for that is once your solution begins to turn slightly pink, you're sort of sitting between this pH of 7 and pH 8 range. So that's why if you ever got a really dark pink like this, you might have been yelled at by your lab instructor to redo it. So that's why we use phenolphthalein. And again, you're just sort of adding until you get to this pink color. Now, the way that we're adding is with a burette. So it's been a while since you've used a burette. So I just want to remind you a couple of things about the burette. Number one is that it fills from the bottom of the burette, which is listed at 50 over here, to the top, which is at 0. So when we take calculations for the volume that we're reading, we always record our initial volume. And if you were exactly here at the top, you would record your volume of 0. And then you're counting how much volume of NaOH that you're adding as you move down. Once your solution turns pink, you close your burette, and then you record the final volume. And the reason this burette starts at 0 is to find the total volume that we're using. We just use the final volume that you stop at minus the initial volume. So for instance, let's just say we started at exactly the 0 point and we titrated and we stopped down here at 6 to find the total volume of NaOH added. We would do final minus initial, or 6 minus 0. That would tell us we use 6 milliliters of NaOH. Now, the other thing about this burette is the precision that we get, or the number of decimal places that you should be using when you calculate these volumes. So remember, you're sort of looking at a meniscus, and this meniscus can sort of fit in between lines on this burette. Now, between the points 0 and 1, okay, this would be a volume of 1 milliliter, but I have tenths place, or 1 digit, that I can also determine based on where these lines are. But there's also this gap in between. So we sort of know to the tenths place exactly our volume, and then we can make one extra guess for a decimal place after this space. So the take-home point is when you record volumes from your burette, you want to have 2 decimal places, 1 decimal place that you know exactly, and 1 that you're making a guess of. Now, you're going to sort of do this standardization 3 times. You'll be given some data for each of those trials. You can calculate based on the balanced chemical reaction, the molarity of your NaOH. You can find a molarity for each of the 3 trials, calculate an average molarity. And then what you're going to do is you're going to perform a new titration where you're taking the value from step number 1, that standardized NaOH, and you're using that to determine a concentration of HCl that is unknown. So we have HCl, which is a strong acid, NaOH, which is a strong base, and hopefully what you know is that when you react a strong acid and a strong base, again, you make this product. We do a neutralization reaction in which we form water and we form a soluble salt. This soluble salt is not going to alter the pH in your solution. So just like the last time, there should be a neutralization that occurs when the concentration of your acid and base are exactly equal to one another. So in this titration, what you're going to do is you're going to start with 25 milliliters of this unknown HCl solution. And again, you're going to start with that sort of in a flask, and you're going to use your standardized NaOH to titrate the HCl. The thing that's going to be slightly different with this procedure is instead of using phenolphthalein to let us know when we've reached that equivalence point, instead we're going to use a pH meter. All right, and what we're going to create is we're going to create something called a titration curve, which will look something like this. So since we're starting with HCl, our initial pH is going to be less than 7 because HCl is a strong acid. And what we begin to do is we begin to drop in the sodium hydroxide, the base. And so the pH begins to rise, and it rises as we add more and more base. Now, what we know about a strong acid and a strong base titration is very quickly, once the concentrations of acids and base get close to one another, there's a very steep jump in our titration curve. So in other words, the pH changes very quickly, even though the volume of base that we're adding is not changing quickly. So this is an important point. You're not going to be adding a lot of volume, but you're going to see a big jump in pH. Now, what we know again about a strong acid, strong base titration is this equivalence point. This equivalence point is going to be exactly at a pH of 7. Now, because this pH changes very rapidly, you might not see the exact volume where pH is 7 on your titration curve. So most likely, you are going to need to estimate where this equivalence point is. But once you have this equivalence point, you know the volume of base that you used to get to that equivalence point. So this is going to be the volume of NaOH. Now you have a volume of NaOH. You already know the standardized concentration of that NaOH, and if you have volume and you have concentration, you can find the number of moles of NaOH. If you have moles of NaOH, you can relate that to moles of HCl, and you use 25 milliliters of HCl. So if you know that number of moles and you know the volume of 25 milliliters, you can find the concentration of HCl, which is the goal of this titration.